Section 15.3, Interpreting and Working with Equilibrium Constants. In this section, we explore two important ideas. Before doing calculations with equilibrium constants, it's valuable to understand what the magnitude of an equilibrium constant can tell us about the relative concentrations of reactants and products of an equilibrium mixture. It's also useful to consider how the magnitude of any equilibrium constant depends on how the chemical equation is expressed. The magnitude of equilibrium constants. Equilibrium constants can vary from very large to very small. The magnitude of the constant provides us with the important information about the composition of an equilibrium mixture. For example, consider the reaction of carbon monoxide gas and chlorine gas at 100 degrees Celsius to form phosgene, a toxic gas used in the manufacture of certain polymers and insecticides. Carbon monoxide gas plus chlorine gas yields phosgene. The concentration constant is the concentration of the phosgene divided by the concentration of the carbon monoxide times the concentration of the chlorine gas. Yields 4.56 times 10 to the 9. For the equilibrium constant to be so large, the numerator of the equilibrium constant expression must be much larger than the denominator. Thus, the equilibrium concentration of the phosgene must be much greater than that of the carbon monoxide or chlorine gas. And in fact, this is just what we find experimentally. We say that this equilibrium lies to the right, that is, towards the product side. Likewise, a very small equilibrium constant indicates that the equilibrium mixture contains mostly reactants. We then say that the equilibrium lies to the left. In general, if the concentration equilibrium constant is much larger than 1, that is a large K, equilibrium lies to the right, and the products predominate. If the equilibrium constant is much less than 1, that is a small k, equilibrium lies to the left and reactants predominate. These situations are summarized in figure 15.7. Remember, opposing rates, not concentration, are equilibrium. Thus, equilibrium constants for different reactions can span a wide range. Figure 15.7, K and the composition of the equilibrium mixture. The equilibrium expression has products in the numerator and reactants in the denominator. When the equilibrium constant is much greater than 1, there are more products than reactants in the equilibrium, and the equilibrium is said to lie to the right. When the equilibrium constant is much less than 1, there are more reactants than products of the equilibrium, and the equilibrium is said to lie at the left. The direction and chemical equation of K. Because an equilibrium can be approached from either direction, the direction in which we write the chemical equation for an equilibrium is arbitrary. For example, we have seen that we can represent dinitrogen tetroxide going to nitrogen dioxide equilibrium as we could equally consider the same equilibrium in terms of the reverse reaction. The equilibrium expression then equals the concentration of the dinitrogen tetroxide over the square of the concentration of the nitrogen dioxide equals 4.72 at 100 Celsius. Equation 517 is just the reciprocal of the equation constant in equation 516. The equilibrium constant expression for a reaction written in one direction is the reciprocal for the one written in the reverse direction. Consequently, the numerical value of the equilibrium constant for the reaction written in one direction is the reciprocal for that in the reverse reaction. Both expressions are equally valid, but it is meaningless to say that the equilibrium constant for the equilibrium between nitrogen dioxide and dinitrogen tetroxide is 4.72 unless we indicate how the equilibrium reaction is written and specify the temperature. Relating chemical equations and equilibrium constants. Just as the equilibrium constants of forward and reverse reactions are reciprocals of each other, the equilibrium constants of reactions associated in other ways are also related. For example, if we were to multiply our original N2O4 going to NO2 equilibrium by 2, we would have 2 dinitrogen tetroxides going to 4 nitrogen dioxides. The equilibrium constant for the expression would be NO2 to the fourth power over N2O4 to the second power, which is simply the square of the equilibrium constant expression for the original equation given in 1510. Because the new equilibrium constant expression equals the original expression squared, the new equilibrium constant equals the original constant squared. In this case, 0.212 squared, or 0.0449 at 100 Celsius. Sometimes, as in problems that utilizes Hess's law, we must use equations made up of two or more steps in the overall process. We obtain the net equation by adding the individual equations and canceling identical terms. Consider the following reactions, their equilibrium constant expressions, and their equilibrium constants at 100 Celsius. K sub C of the first is 0.014, K sub C of the second is 7.2. The net sum of these two equations are, and the equilibrium constant expression from the net equation is the product of the expressions for the individual steps. Because the equilibrium constant expression for the net equation is the product of two equilibrium constant expressions, the equilibrium constant for the net equation is the product of two individual equilibrium constants. K sub C equals 0.014 times 7.2 equals 0.10. To summarize, the equilibrium constant of a reaction in the reverse reaction is the inverse of the equilibrium constant of the reaction in the forward direction. The equilibrium constant of a reaction that's been multiplied by a number is the equilibrium constant raised to the power equal to that number. The equilibrium constant for a net reaction made up of two or more steps is the product of the equilibrium constants for the individual steps.